We'll now continue our study of latches with the data latch. We had previously looked at the set reset latch. It had some indeterminate states, which made it not good to use. So the D latch is going to get rid of those indeterminate states. We'll take a look at how it behaves here. We've added then to the SR latch. If you look at this section here, right here, this is an SR latch made with NAND gates. We've added on some additional gates and an enable signal. We'll have one input to this named D, right, when the circuit is disabled. So when enable is equal to 0, it doesn't matter what value is on D. We'll see that there's no change in state, meaning whatever Q is now, it will be the same in the next state. Only when the circuit is enabled, so when enable is a 1, will the next state change. And the next state, Q, will always be dependent on D. It won't be dependent on the present state. So when D is a 0 and enable is a 1, Q will be a 0. When D is a 1, enable is a 1, Q will be 1 for our data latch. So let's take a look at this. I've drawn this circuit out in Quartus here so that we can actually then make some changes. All right, we said there's a no state change when enable is 0. So here I'm just going to use the text tool, right, to type in a 0. And let's start with the fact that Q is a 0, right? So if Q is a 0, that would mean our Q naught should be a 1. And let's see what happens then. Okay, if D is a 0 and Q is a 1, let's take a look at this circuit. So 0 ANDed with 0 gives us a 0, inverted gives us a 1. In this point, 0 ANDed with 1 still gives us a 0, inverted then gives us a 1. Right, so 1 ANDed with, well, this input coming in here is a 0, right? Because we said Q is a 0. I need to type the right thing. Right, 1 ANDed with 0 still gives us a 0. Inverted gives us a 1. So our input here is 1. 1 ANDed with 1 gives us a 1, but inverted gives us a 0. Right. We end up then with an output of 0 still on Q. We did not change that state, so it held its state. Right. It doesn't matter either then if when Q is a 0, if D happens to be a 1, right, that would make D naught a 0. Let's look at this. 0 ANDed with 1 is a 0, inverted gives us a 1. 0 ANDed with 0 is a 0, inverted gives us a 1. 1 ANDed with 0 is a 0, inverted gives us a 1. 1 ANDed with 1 gives us a 1, but inverted gives us a 0. Right? Once again, Q does not change state as long as the circuit is disabled. Enable then happens to have a value of 0, or a level of 0 in this case. Similarly, let's take a look at, let's see what happens when D is 0, and that would make D naught a 1, and Q happen to be a 1. So Q is a 1, that's its present state, Q naught would be a 0. The circuit's still disabled, D is a 0, 0 ANDed with 0 is a 0, but inverted gives us a 1, 0 ANDed with 1 is a 0, inverted gives us a 1. So if this is a 1 here in the present state, right, this must be a 1. 1 ANDed with 1 gives us 1, inverted gives us a 0. So that gives us a 0 here. 0 ANDed with 1 gives us a 0, inverted gives us a 1. Everything becomes stable, and our output does not change. We can go through the same exercise then when D is a 1. Right, D naught's a 0. We said Q happened to be a 1. We'll see that state does not change as long as enables a 0. 1 ANDed with 0 gives us a 0. Inverted gives us a 1. 0 ANDed with 0 gives us a 0. Inverted gives us a 1. 1 ANDed with 1 gives us 1. Inverted gives us a 0. 0 ANDed with 1 gives us a 0. Inverted gives us a 1. We do not change state. So when enable signal is a 0, right, doesn't matter what D is, we don't have any state change. Now let's take a look at what happens when, let's say that Q is a 0, right, Q naught's a 1. When D is a 0, D is a 0, we're going to change enable to a 1. D naught then must be a 1. Right, we should see that Q will be whatever the value of D is. Right. So let's take a look now. 1 ANDed with 0 gives us a 0. Inverted gives us a 1. 1 ANDed with 1 gives us a 1. Inverted gives us a 0. Right? Since we said our Q was a 0, the input here is a 0. 0 ANDed with 0 gives us a 0. Inverted gives us a 1. Okay, then this output becomes a 1. 1 ended with 1 gives us a 1. Inverted gives us a 0. Right? So we end up with a stable state where Q is a 0, Q naught's a 1. Right? And notice then, D is a 0, Q next is a 0 whenever enable's a 1. Similarly, if D becomes a 1, D naught becomes a 0. Right? So 1 ended with 1 gives us a 1. Inverted gives us a 0 here. 1 ended with 0 here gives us a 0. Inverted gives us a 1 here. Right? So 1 ended with 0 gives us a 0. Right? Inverted gives us a 1, so we have a 1 here. 1 ended with 0 gives us a 0. Inverted gives us a 1. That drives this to a 1. 1 ended with 1 gives us a 1, but inverted gives us a 0. Right? Causing this change to happen here. 0, 0 ended with 0 still gives us a 0. Inverted gives us a 1. So finally we reach a stable state where Q is a 1, Q naught's a 0. So the circuit's enabled, D is a 1, Q is a 1. So that's the way a D latch behaves. What you want to remember is whenever it's enabled, then Q in the next state will be whatever the input D is. Right? When it's disabled, it will not change state. Right? Q will hold its state. All right, let's go back then. And that was our functional, our functional table here, right, that we just discussed. Let's look at the state table. So the state table has 3 inputs. It has enable in the current state, so enable at time t, enable in the present state, D in the present state, Q in the present state. So we have these 3 inputs, so we have 8 binary combinations. Right? Our output of the circuit is Q in the next state at some time t plus delta t when we take that measurement. Notice as long as enables a 0, the output, Q in the next state, will mirror Q in the present state. So 0 here, 0 here, 1 here, Q next 1, Q present 0, Q next 0, Q present 1, Q next 1, as long as enable is a 0. But now, when enable is a 1, right, we said our behavior is Q in the next state should be D in the present state. So in both of these cases, D is a 0, so Q next will be a 0. Did not matter what was on Q in the present. Similarly, when D is a 1, then our output Q next will be the value of D, ignoring then the present state. That's the behavior we said we wanted to specify. That's how we decide where our 0s and 1s go. What we do then is we go ahead and K-map this. Right? We go ahead and map all these 0s and 1s. Then over here, so here's the same table. Right? In this case, now we see that we've got 0, 0, 1, 0, 1, 1. So 0, 0, 1, 0, 1, 1 are both 1s. And then 1, 1, 0. So this is 1, 1, 0. This is 1, 1, 1. But we've got 1s here. We form these 2 groups. And you can see then we have enables a 0. So enable not ended with Q. Enable not ended with Q, right, at time t. Or with enables a 1 ended with D. Right? So we can see then, right, when enables a 0, the output will be whatever Q is. Or when enables a 1, the output will be whatever D is. And we tend to write these as Q plus as Q in the next state. We start dropping the T's and delta T's. It's easier to read. Right? So that becomes the next state equation, also known as the characteristic equation of a D latch. Right? It's sensitive to the level of enable. So a gated D latch is also called a transparent latch, meaning whatever's on D becomes the output to Q when it's enabled. Right? It's typically used in I/O ports or asynchronous systems. So I/O ports could be, an example is a keyboard. Your keyboard buffer uses latches. So if you press a key and it wants to keep track of what key was pressed, it's going to keep track of, if I press the K key, it's going to keep track of the fact that I pressed the K key and store that information in memory. Right. Now let's take a look then at a simulation. Right. If we were to draw out the behavior here, right, we could take a look at the simulation, but I'd rather just go ahead and run this with Quartus. Escape out of PowerPoint here, and I'm going here in Quartus. Here I used one of the libraries. So the library then has a latch. So if I say insert symbol, and I bring up the symbol library, under storage, there is this D latch. And that's what I was using here. That's where I got that. And I just hooked up 2 input pins that I named D and enable. Our output is named Q. Right. I'm going to go ahead then and create a simulation of this. So let me open this up. All right, I set it for 80 nanoseconds. I've got my input D and my input enable. Well, the clock period then I used for enable happened to be 10 nanoseconds. I believe I was using 15 or maybe 17 for D. I just didn't want D. I'm trying to avoid having D transition at the same time as my clock edge does. All right, so I'm going to run the functional simulation here. And all right, showed up on my other screen. Here we go. Here's the output. What I want you to observe is when the simulation started at time t equals 0, the output on Q was unknown. As long as enable is low, we hold our state. So notice the unknown state held until enable became high. At which point in time, right at 5 nanoseconds when enable became high, our signal D happened to be a 0, so our output Q was a 0. Right? And then as long as enable's high, our output's going to follow whatever's on D. So at 8.5 nanoseconds, D transitioned to high. Notice our output Q transitions to high. Right? Now, when enable goes low, D happened to be a 1 or high at that time. So this stays high until our circuit's enabled again. So at 15 nanoseconds, when this enable goes back to a 1, D happens to be high, so the circuit stays high. Notice here, enable's still a 1 at 17 nanoseconds. D drops back to 0, so our output Q drops back to 0. When the enable level goes back to 0, we're going to hold our state, so Q is going to stay 0 until such time as the enable goes high. When the enable goes high, D is still a 0, so our output Q is a 0. Right. D goes high at 25.5 nanoseconds. Enable's still a 1, so our output becomes a 1. Right. So you can trace this all the way across here and see that whenever enable's a 0, Q holds its state. Right. Whenever enable's a 1, the output Q becomes whatever the input D is. So Q is just always equal to D whenever the circuit's enabled. When it's not enabled, it just holds its current state. All right. I'm going to close that down. All right. Just about done. D latches are handy to use. All right. We have just one other thing that I really want to say about them is one thing we don't do is we don't connect these together, right, with a common clock. So in this particular circuit right here, I've got this D latch and this D latch. And what I mean by connect together is we don't have the input of this D latch be dependent on this one and share a common clock. So clock in this case is also enable. Remember, a clock can be a 0 or a 1. When the clock is 0, right, this Q and this Q over here both hold their state. When the clock becomes a 1, then whatever's on this D, right, flows through to this Q, and then its output becomes the input of this. Well, some of this is hard to time because you've got, if you might have your input level changing and your output levels changing, it's subject to error when we try to measure when we have several of these chained together. So we do use several of these to represent memory, but we just don't have the input of one being dependent on the output of the other. But later when we create some registers, we'll use some latches then, and we'll wire them in a way that we can create memory. It just won't have one input dependent on the output of another. So that causes error when they share a common clock, and almost everything in our system will share a common clock. Our next lecture topic will be on flip-flops. That's what we'll be using quite a bit from now on. That will be in the next video.